The quality of hypothesis test. The same idea can be expressed in terms of the rate of correct results and therefore used to minimize error rates and improve the quality of hypothesis test. To reduce the probability of committing a type 1 error, making the alpha value more stringent is both simple and efficient. To decrease the probability of committing a type 2 error, which is closely associated with analyses power, either increasing the test sample size or relaxing the alpha level could increase the analyses power. A test statistic is robust if the type 1 error rate is controlled. Varying different threshold cutoff values could also be used to make the test either more specific or more sensitive, which in turn elevates the test quality. For example, imagine a medical test, in which an experimenter might measure the concentration of a certain protein in the blood sample. The experimenter could adjust the threshold black vertical line in the figure, and people would be diagnosed as having diseases if any number is detected above this certain threshold. According to the image, changing the threshold would result in changes in false positives and false negatives, corresponding to movement on the curve. Example. Since in a real experiment it is impossible to avoid all type 1 and type 2 errors, it is important to consider the amount of risk one is willing to take to falsely reject H0 or accept H0. The solution to this question would be to report the p-value or significance level alpha of the statistic. For example, if the p-value of a test statistic result is estimated at 0.0596, then there is a probability of 5.96% that we falsely reject H0. Or, if we say, the statistic is performed at level alpha, like 0.05, then we allow to falsely reject H0 at 5%. A significance level alpha of 0.05 is relatively common, but there is no general rule that fits all scenarios. Vehicle speed measuring. The speed limit of a freeway in the United States is 120 km per hour, 75 miles per hour. A device is set to measure the speed of passing vehicles. Suppose that the device will conduct 3 measurements of the speed of a passing vehicle, recording as a random sample x1, x2, x3. The traffic police will or will not find the drivers depending on the average speed. That is to say, the test statistic. In addition, we suppose that the measurements x1, x2, x3 are modeled as normal distribution and mu, 2. Then, t should follow and mu, 2, and the parameter mu represents the true speed of passing vehicle. In this experiment, the null hypothesis H0 and the alternative hypothesis H1 should be H0, mu equals 120 against H1, mu greater than 120. If we perform a statistic level at alpha equals 0.05, then a critical value C should be calculated to solve according to change of units rule for the normal distribution. Referring to Z table, we can get here, the critical region. That is to say, if the recorded speed of a vehicle is greater than critical value 121.9, the driver will be fined. However, there are still 5% of the drivers are falsely fined since the recorded average speed is greater than 121.9 but the true speed does not pass 120, which we say, a type 1 error. The type 2 error corresponds to the case that the true speed of a vehicle is over 120 km per hour but the driver is not fined. For example, if the true speed of a vehicle mu equals 125, the probability that the driver is not fined can be calculated as. Which means, if the true speed of a vehicle is 125, the driver has the probability of 0.36% to avoid the fine when the statistic is performed at level alpha equals 0.05, since the recorded average speed is lower than 121.9. If the true speed is closer to 121.9 than 125, then the probability of avoiding the fine will also be higher. The trade-offs between type 1 error and type 2 error should also be considered. That is, in this case, if the traffic police do not want to falsely fine innocent drivers, the level alpha can be set to a smaller value, like 0.01. However, if that is the case, more drivers whose true speed is over 120 km per hour, like 125, would be more likely to avoid the fine. Etymology. In 1928, Jerzy Neyman 1894-1981, and Egan Pearson 1895-1980, both eminent statisticians, discussed the problems associated with deciding whether or not a particular sample may be judged as likely to have been randomly drawn from a certain population. 6. And, as Florence Nightingale David remarked, it is necessary to remember the adjective random, in the term, random sample, should apply to the method of drawing the sample and not to the sample itself. 7. They identified 2 sources of error, namely a. The error of rejecting a hypothesis that should have not been rejected, and b. The error of failing to reject a hypothesis that should have been rejected. In 1930, they elaborated on these 2 sources of error, remarking that in testing hypotheses 2 considerations must be kept in view. We must be able to reduce the chance of rejecting a true hypothesis to as low a value as desired. The test must be so devised that it will reject the hypothesis tested when it is likely to be false. In 1933, they observed that these problems are rarely presented in such a form that we can discriminate with certainty between the true and false hypothesis. They also noted that, in deciding whether to fail to reject, or reject a particular hypothesis amongst a set of alternative hypotheses, H1, H2, it was easy to make an error. And these errors will be of 2 kinds. I. We reject H0, i.e., the hypothesis to be tested when it is. I. We reject H0, i.e., the hypothesis to be tested when it is true, H2. We fail to reject H0 when some alternative hypothesis HA or H1 is true. Theory or various notations for the alternative. In all of the papers co-written by Neyman and Pearson, the expression H0 always signifies the hypothesis to be tested. In the same paper they call these 2 sources of error, errors of type 1 and errors of type 2 respectively. 9. Related terms. Null hypothesis. It is standard practice for statisticians to conduct tests in order to determine whether or not a speculative hypothesis concerning the observed phenomena of the world or its inhabitants can be supported. The results of such testing determine whether a particular set of results agrees reasonably or does not agree with the speculated hypothesis. On the basis that it is always assumed, by statistical convention, that the speculated hypothesis is wrong, and the so-called null hypothesis, that the observed phenomena simply occur by chance, and that, as a consequence, the speculated agent has no effect, the test will determine whether this hypothesis is right or wrong. This is why the hypothesis under test is often called the null hypothesis, most likely, coined by Fisher, 1935, page 19, because it is this hypothesis that is to be either nullified or not nullified by the test. When the null hypothesis is nullified, it is possible to conclude that data support the alternative hypothesis, which is the original speculated one. The consistent application by statisticians of Neyman and Pearson's convention of representing the hypothesis to be tested, or the hypothesis to be nullified, with the expression H0 has led to circumstances where many understand the term, the null hypothesis, as meaning, the null hypothesis, a statement that the results in question have arisen through chance. This is not necessarily the case. The key restriction, as per Fisher, 1966, is that the null hypothesis must be exact, that is free from vagueness and ambiguity, because it must supply the basis of the problem of distribution, of which the test of significance is the solution. 10. As a consequence of this, in experimental science the null hypothesis is generally a statement that a particular treatment has no effect. In observational science, it is that there is no difference between the value of a particular measured variable and that of an experimental prediction. Statistical significance. If the probability of obtaining a result as extreme as the one obtained, supposing that the null hypothesis were true, is lower than a pre-specified cutoff probability, for example, 5%, then the result is said to be statistically significant and the null hypothesis is rejected. British statistician Sir Ronald Aylmer Fisher, 1890–1962, stressed that the null hypothesis is never proved or established, but is possibly disproved, in the course of experimentation. Every experiment may be said to exist only in order to give the facts a chance of disproving the null hypothesis. Fisher, 1935, page .19. Application domains. Medicine. In the practice of medicine, the differences between the applications of screening and testing are considerable. Medical screening. Screening involves relatively cheap tests that are given to large populations, none of whom manifest any clinical indication of disease, e.g., Pap smears. Testing involves far more expensive, often invasive, procedures that are given only to those who manifest some clinical indication of disease, and are most often applied to confirm a suspected diagnosis. For example, most states in the U.S. require newborns to be screened for phenylketonuria and hypothyroidism, among other congenital disorders. Hypothesis: the newborns have phenylketonuria and hypothyroidism. Null hypothesis H0: the newborns do not have phenylketonuria and hypothyroidism. Type 1 error, false positive: the true fact is that the newborns do not have phenylketonuria and hypothyroidism, but we consider they have the disorders according to the data. Type 2 error, false negative: the true fact is that the newborns have phenylketonuria and hypothyroidism, but we consider they do not have the disorders according to the data. Although they display a high rate of false positives, the screening tests are considered valuable because they greatly increase the likelihood of detecting these disorders at a far earlier stage. The simple blood tests used to screen possible blood donors for HIV and hepatitis have a significant rate of false positives. However, physicians use much more expensive and far more precise tests to determine whether a person is actually infected with either of these viruses. Perhaps the most widely discussed false positives in medical screening come from the breast cancer screening procedure mammography. The U.S. rate of false positive mammograms is up to 15%, the highest in world. One consequence of the high false positive rate in the U.S. is that, in any 10-year period, half of the American women screened receive a false positive mammogram. False positive mammograms are costly, with over $100 million spent annually in the U.S. on follow-up testing and treatment. They also cause women unneeded anxiety. As a result of the high false positive rate in the U.S., as many as 90–95% of women who get a positive mammogram do not have the condition. The lowest rate in the world is in the Netherlands, 1%. The lowest rates are generally in Northern Europe, where mammography films are read twice and a high threshold for additional testing is set. The high threshold decreases the power of the test. The ideal population screening test would be cheap, easy to administer, and produce 0 false negatives, if possible. Such tests usually produce more false positives, which can subsequently be sorted out by more sophisticated and expensive testing. Medical testing. False negatives and false positives are significant issues in medical testing. Hypothesis: the patients have a specific disease. Null hypothesis H0: the patients do not have a specific disease. Type 1 error, false positive: the true fact is that the patients do not have a specific disease, but the physician judges the patient is ill according to the test reports. Type 2 error, false negative: the true fact is that the disease is actually present, but the test reports provide a falsely reassuring message to patients and physicians that the disease is absent. False positives can also produce serious and counterintuitive problems when the condition being searched for is rare, as in screening. If a test has a false positive rate of 1 in 10,000, but only 1 in a million samples, or people, is a true positive, most of the positives detected by that test will be false. The probability that an observed positive result is a false positive may be calculated using Bayes' theorem. False negatives produce serious and counterintuitive problems, especially when the condition being searched for is common. If a test with a false negative rate of only 10% is used to test a population with a true occurrence rate of 70%, many of the negatives detected by the test will be false. This sometimes leads to inappropriate or inadequate treatment of both the patient and their disease. A common example is relying on cardiac stress tests to detect coronary atherosclerosis, even though cardiac stress tests are known to only detect limitations of coronary artery blood flow due to advanced stenosis. Biometrics. Biometric matching, such as for fingerprint recognition, facial recognition or iris recognition, is susceptible to type 1 and type 2 errors. Hypothesis. The input does not identify someone in the searched list of people. Null hypothesis. The input does identify someone in the searched list of people. Type 1 error, false reject rate. The true fact is that the person is someone in the searched list, but the system concludes that the person is not according to the data. Type 2 error, false match rate. The true fact is that the person is not someone in the searched list, but the system concludes that the person is someone whom we are looking for according to the data. The probability of type 1 errors is called the false reject rate, FRR, or false non-match rate, FNMR, while the probability of type 2 errors is called the false accept rate, FAR, or false match rate, FMR. If the system is designed to rarely match suspects, then the probability of type 2 errors can be called the false alarm rate. On the other hand, if the system is used for validation and acceptance as the norm, then the FAR is a measure of system security, while the FRR measures user inconvenience level. Security screening. False positives are routinely found every day in airport security screening, which are ultimately visual inspection systems. The installed security alarms are intended to prevent weapons being brought onto aircraft, yet they are often set to such high sensitivity that they alarm many times a day for minor items, such as keys, belt buckles, loose change, mobile phones, and tacks in shoes. Hypothesis. The item is a weapon. Null hypothesis. The item is not a weapon. Type 1 error, false positive. The true fact is that the item is not a weapon, but the system still sounds an alarm. Mathematics portal. Type 2 error, false negative. The true fact is that the item is a weapon, but the system keeps silent at this time. The ratio of false positives identifying an innocent traveler as a terrorist to true positives detecting a would-be terrorist is, therefore, very high, and because almost every alarm is a false positive, the positive predictive value of these screening tests is very low. The relative cost of false results determines the likelihood that test creators allow these events to occur. As the cost of a false negative in this scenario is extremely high, not detecting a bomb being brought onto a plane could result in hundreds of deaths, whilst the cost of a false positive is relatively low. A reasonably simple further inspection, the most appropriate test is one with a low statistical specificity but high statistical sensitivity, one that allows a high rate of false positives in return for minimal false negatives. Computers. The notions of false positives and false negatives have a wide currency in the realm of computers and computer applications, including computer security, spam filtering, malware, optical character recognition, and many others. For example, in the case of spam filtering. Hypothesis. The message is spam. Null hypothesis. The message is not spam. Type 1 error, false positive. Spam filtering or spam blocking techniques wrongly classify a legitimate email message as spam and, as a result, interfere with its delivery. Type 2 error, false negative. Spam email is not detected as spam, but is classified as non-spam. While most anti-spam tactics can block or filter a high percentage of unwanted emails, doing so without creating significant false positive results is a much more demanding task. A low number of false negatives is an indicator of the efficiency of spam filtering. Student's t-test. Student's t-test is a statistical test used to test whether the difference between the response of two groups is statistically significant or not. It is any statistical hypothesis test in which the test statistic follows a student's t-distribution under the null hypothesis. It is most commonly applied when the test statistic would follow a normal distribution if the value of a scaling term in the test statistic were known. Typically, the scaling term is unknown and is therefore a nuisance parameter. When the scaling term is estimated based on the data, the test statistic, under certain conditions, follows a student's t-distribution. The t-test's most common application is to test whether the means of two populations are significantly different. In many cases, a z-test will yield very similar results to a t-test because the latter converges to the former as the size of the dataset increases. History. William Seeley-Gossett, who developed the t-statistic and published it under the pseudonym of student. The term t-statistic is abbreviated from hypothesis test statistic. 1. In statistics, the t-distribution was first derived as a posterior distribution in 1876 by Helmer, 2, 3, 4, and Luroth. 5, 6, 7. The t-distribution also appeared in a more general form as Pearson type 4 distribution in Carl Pearson's 1895 paper. 8. However, the t-distribution, also known as student's t-distribution, gets its name from William Seeley-Gossett, who first published it in English in 1908 in the scientific journal Biometrica using the pseudonym student. 9. 10. Because his employer preferred staff to use pen names when publishing scientific papers. 11. Gossett worked at the Guinness Brewery in Dublin, Ireland, and was interested in the problems of small samples, for example, the chemical properties of barley with small sample sizes. Hence a second version of the etymology of the term student is that Guinness did not want their competitors to know that they were using the t-test to determine the quality of raw material. Although it was William Gossett after whom the term student is penned, it was actually through the work of Ronald Fisher that the distribution became well known as student's distribution, 12, and student's t-test. Gossett devised the t-test as an economical way to monitor the quality of stout. The t-test work was submitted to and accepted in the journal Biometrica and published in 1908. 9. Guinness had a policy of allowing technical staff leave for study, so-called study leave, which Gosset used during the first 2 terms of the 1906-1907 academic year in Professor Karl Pearson's biometric laboratory at University College London. 13. Gosset's identity was then known to fellow statisticians and to editor-in-chief Karl Pearson. 14. Uses. 1 sample t-test. A one-sample student's t-test is a location test of whether the mean of a population has a value specified in a null hypothesis. In testing the null hypothesis that the population mean is equal to a specified value μ0, one uses a statistic. Where is the sample mean? S is the sample standard deviation and n is the sample size. The degrees of freedom used in this test are n-1. Although the parent population does not need to be normally distributed, the distribution of the population of sample means is assumed to be normal. By the central limit theorem, if the observations are independent and the second moment exists, then will be approximately normal. 2 sample t-tests. Type 1 error of unpaired and paired 2 sample t-tests is a function of the correlation. The simulated random numbers originate from a bivariate normal distribution with a variance of 1. The significance level is 5% and the number of cases is 60. Power of unpaired and paired 2 sample t-tests is a function of the correlation. The simulated random numbers originate from a bivariate normal distribution with a variance of 1 and a deviation of the expected value of 0.4. The significance level is 5% and the number of cases is 60. A 2 sample location test of the null hypothesis such that the means of 2 populations are equal. All such tests are usually called student's t-tests, though strictly speaking that name should only be used if the variances of the 2 populations are also assumed to be equal. The form of the test used when this assumption is dropped is sometimes called Welch's t-test. These tests are often referred to as unpaired or independent samples t-tests, as they are typically applied when the statistical units underlying the 2 samples being compared are non-overlapping. 15. 2 sample t-tests for a difference in means involve independent samples, unpaired samples, or paired samples. Paired t-tests are a form of blocking, and have greater probability of avoiding a type 2 error, also known as a false negative, than unpaired tests when the paired units are similar with respect to noise factors, C confounder, that are independent of membership in the 2 groups being compared. 16. In a different context, paired t-tests can be used to reduce the effects of confounding factors in an observational study. Independent, unpaired, samples. The independent samples t-test is used when 2 separate sets of independent and identically distributed samples are obtained, and 1 variable from each of the 2 populations is compared. For example, suppose we are evaluating the effect of a medical treatment, and we enroll 100 subjects into our study, then randomly assign 50 subjects to the treatment group and 50 subjects to the control group. In this case, we have 2 independent samples and would use the unpaired form of the t-test. Paired samples. Paired samples t-tests typically consist of a sample of matched pairs of similar units, or 1 group of units that has been tested twice, a repeated measures t-test. A typical example of a repeated measures t-test would be where subjects are tested prior to a treatment, say for high blood pressure, and the same subjects are tested again after treatment with a blood pressure lowering medication. By comparing the same patient's numbers before and after treatment, we are effectively using each patient as their own control. That way the correct rejection of the null hypothesis, here, of no difference made by the treatment, can become much more likely, with statistical power increasing simply because the random interpotient variation has now been eliminated. However, an increase of statistical The independent samples t-test is used when 2 separate sets of independent and identically distributed samples are obtained, and 1 variable from each of the 2 populations is compared. For example, suppose we are evaluating the effect of a medical treatment, and we enroll 100 subjects into our study, then randomly assign 50 subjects to the treatment group and 50 subjects to the control group. In this case, we have 2 independent samples and would use the unpaired form of the t-test. Paired samples. Paired samples t-tests typically consist of a sample of matched pairs of similar units, or 1 group of units that has been tested twice, a repeated measures t-test. A typical example of the repeated measures t-test would be where subjects are tested prior to a treatment, say for high blood pressure, and the same subjects are tested again after treatment with a blood pressure lowering medication. By comparing the same patient's numbers before and after treatment, we are effectively using each patient as their own control. That way the correct rejection of the null hypothesis, here, of no difference made by the treatment, can become much more likely, with statistical power increasing simply because the random interpotient variation has now been eliminated. However, an increase of statistical power comes at a price. More tests are required, each subject having to be tested twice. Because half of the sample now depends on the other half, the paired version of student's t-test has only n. 2-1 degree of freedom, with n being the total number of observations. Pairs become individual test units, and the sample has to be doubled to achieve the same number of degrees of freedom. Normally, there are n-1 degree of freedom, with n being the total number of observations. 17. A paired samples t-test based on a matched pairs sample results from an unpaired sample that is subsequently used to form a paired sample by using additional variables that were measured along with the variable of interest. 18. The matching is carried out by identifying pairs of values consisting of 1 observation from each of the 2 samples, where the pair is similar in terms of other measured variables. This approach is sometimes used in observational studies to reduce or eliminate the effects of confounding factors. Paired samples t-tests are often referred to as dependent samples t-tests. Assumptions. Most test statistics have a form T equals Z S, where Z and S are functions of the data. Z may be sensitive to the alternative hypothesis, i.e., its magnitude tends to be larger when the alternative hypothesis is true, whereas S is a scaling parameter that allows the distribution of t to be determined. As an example, in the one-sample t-test, whereas the sample mean from a sample x1, x2, xn, of size n, S is the standard error of the mean, is the estimate of the standard deviation of the population, and mu is the population mean. The assumptions underlying a t-test in the simplest form above are that x follows a normal distribution with mean mu and variance sigma 2 n. S2 n-1, sigma 2 follows a chi2 distribution with n-1 degree of freedom. This assumption is met when the observations used for estimating S2 come from a normal distribution, and d. For each group, Z and S are independent. In the t-test comparing the means of two independent samples, the following assumptions should be met. The means of the two populations being compared should follow normal distributions. Under weak assumptions, this follows in large samples from the central limit theorem, even when the distribution of observations in each group is non-normal. 19. If using students' original definition of the t-test, the two populations being compared should have the same variance testable using F-test, Levene's test, Bartlett's test, or the Brown-Forsyth test, or accessible graphically using a QQ plot. If the sample sizes in the two groups being compared are equal, students' original t-test is highly robust to the presence of unequal variances. 20. Welch's t-test is insensitive to equality of the variances regardless of whether the sample sizes are similar. The data used to carry out the test should either be sampled independently from the two populations being compared or be fully paired. This is in general not testable from the data, but if the data are known to be dependent, e.g. paired by test design, a dependent test has to be applied. For partially paired data, the classical independent t-tests may give invalid results as the test statistic might not follow a t-distribution, while the dependent t-test is suboptimal as it discards the unpaired data. 21. Most two-sample t-tests are robust to all but large deviations from the assumptions. 22. For exactness, the t-test and z-test require normality of the sample means, and the t-test additionally requires that the sample variance follows a scaled chi2 distribution, and that the sample mean and sample variance be statistically independent. Normality of the individual data values is not required if these conditions are met. By the central limit theorem, sample means of moderately large samples are often well approximated by a normal distribution even if the data are not normally distributed. However, the sample size required for the sample means to converge to normality depends on the skewness of the distribution of the original data. The sample can vary from 30 to 100 or higher values depending on the skewness. 23, 24, f. For non-normal data, the distribution of the sample variance may deviate substantially from a chi2 distribution. However, if the sample size is large, Slutsky's theorem implies that the distribution of the sample variance has little effect on the distribution of the test statistic. That is, as sample size increases. As per the central limit theorem, as per the law of large numbers. If the approach for equal variances discussed chi-squared test. A chi-squared test, also chi-square or chi-2 test, is a statistical hypothesis test used in the analysis of contingency tables when the sample sizes are large. In simpler terms, this test is primarily used to examine whether two categorical variables, two dimensions of the contingency table, are independent in influencing the test statistic values within the table. 1. The test is valid when the test statistic is chi-squared distributed under the null hypothesis, specifically Pearson's chi-squared test and variance thereof. Pearson's chi-squared test is used to determine whether there is a statistically significant difference between the expected frequencies and the observed frequencies in one or more categories of a contingency table. For contingency tables with smaller sample sizes, a Fisher's exact test is used instead. Chi-squared distribution, showing chi2 on the x-axis and p-value, right tail probability, on the y-axis. In the standard applications of this test, the observations are classified into mutually exclusive classes. If the null hypothesis that there are no differences between the classes in the population is true, the test statistic computed from the observations follows a chi2 frequency distribution. The purpose of the test is to evaluate how likely the observed frequencies would be assuming the null hypothesis is true. Test statistics that follow a chi2 distribution occur when the observations are independent. There are also chi2 tests for testing the null hypothesis of independence of a pair of random variables based on observations of the pairs. Chi-squared tests often refers to tests for which the distribution of the test statistic approaches the chi-2 distribution asymptotically, meaning that the sampling distribution, if the null hypothesis is true, of the test statistic approximates the chi-squared distribution more and more closely as sample sizes increase. History. In the 19th century, statistical analytical methods were mainly applied in biological data analysis, and it was customary for researchers to assume that observations followed a normal distribution, such as Sir George Arion Mansfield Merriman, whose works were criticized by Karl Pearson in his 1900 paper. 2. At the end of the 19th century, Pearson noticed the existence of significant skewness within some biological observations. In order to model the observations regardless of being normal or skewed, Pearson, in a series of articles published from 1893 to 1916, 3, 4, 5, 6 devised the Pearson distribution, a family of continuous probability distributions, which includes the normal distribution and many skewed distributions, and proposed a method of statistical analysis consisting of using the Pearson distribution to model the observation and performing a test of goodness of fit to determine how well the model really fits to the observations. Pearson's chi-squared test. In 1900, Pearson published a paper, 2, on the chi-2 test, which is considered to be one of the foundations of modern statistics. 7. In this paper, Pearson investigated a test of goodness of fit. Suppose that n observations in a random sample from a population are classified into k mutually exclusive classes with respective observed numbers of observations xi, for I equals 1, 2, k, and a null hypothesis gives the probability pi that an observation falls into the ith class. So we have the expected numbers mi equals npi for all I, where Pearson proposed that, under the circumstance of the null hypothesis being correct, is n right pointing arrow infinity the limiting distribution of the quantity given below as the chi-2 distribution. Pearson dealt first with the case in which the expected numbers mi are large enough known numbers in all cells assuming every observation xi may be taken as normally distributed, and reached the result that, in the limit as n becomes large, x2 follows the chi-2 distribution with k-1 degree of freedom. However, Pearson next considered the case in which the expected numbers depended on the parameters that had to be estimated from the sample, and suggested that, with the notation of mi being the true expected numbers and mi being the estimated expected numbers, the difference will usually be positive and small enough to be omitted. In a conclusion, Pearson argued that if we regarded x2 as also distributed as chi-2 distribution with k-1 degree of freedom, the error in this approximation would not affect practical decisions. This conclusion caused some controversy in practical applications and was not settled for 20 years until Fisher's 1922 and 1924 papers. 8. 9. Other examples of chi-squared tests. One test statistic that follows a chi-squared distribution exactly is the test that the variance of a normally distributed population has a given value based on a sample variance. Such tests are uncommon in practice because the true variance of the population is usually unknown. However, there are several statistical tests where the chi-squared distribution is approximately valid. Fisher's exact test. For an exact test used in place of the 2 times 2 chi-squared test for independence, see Fisher's exact test. Binomial test. For an exact test used in place of the 2 times 1 chi-squared test for goodness of fit, see binomial test. Other chi-squared tests. Cochran-Mantel-Heinzel chi-squared test. McNemar's test, used in certain 2 times 2 tables with pairing. Tukey's test of additivity. The Portmanteau test in time series analysis, testing for the presence of autocorrelation likelihood ratio tests in general statistical modeling. For the Portmanteau test in time series analysis, testing for the presence of autocorrelation likelihood ratio tests in general statistical modeling, for testing whether there is evidence of the need to move from a simple model to a more complicated one, where the simple model is nested within the complicated one. Yates's correction for continuity. Using the chi-squared distribution to interpret Pearson's chi-squared statistic requires one to assume that the discrete probability of observed binomial frequencies in the table can be approximated by the continuous chi-squared distribution. This assumption is not quite correct and introduces some error. To reduce the error in approximation, Frank Yates suggested a correction for continuity that adjusts the formula for Pearson's chi-squared test by subtracting 0.5 from the absolute difference between each observed value and its expected value in a 2 times 2 contingency table. 10th, this reduces the chi-squared value obtained and thus increases its p-value. Chi-squared test for variance in a normal population. If a sample of size n is taken from a population having a normal distribution, then there is a result, C distribution of the sample variance, which allows a test to be made of whether the variance of the population has a predetermined value. For example, a manufacturing process might have been in stable condition for a long period, allowing a value for the variance to be determined essentially without error. Suppose that a variant of the process is being tested, giving rise to a small sample of n product items whose variation is to be tested. The test statistic t in this instance could be set to be the sum of squares about the sample mean, divided by the nominal value for the variance, i.e. the value to be tested is holding. Then t has a chi-squared distribution with n-1 degree of freedom. For example, if the sample size is 21, the acceptance region for t with a significance level of 5% is between 9.59 and 34.17. Suppose there is a city of 1 million residents with 4 neighborhoods, A, B, C, and D. A random sample of 650 residents of the city is taken and their occupation is recorded as white collar, blue collar, or no collar. The null hypothesis is that each person's neighborhood of residence is independent of the person's occupational classification. The data are tabulated as ABCD total. White collar 906010495349, blue collar 305051201510, no collar 304045351550. Total 150,150,200,150,650. Let us take the sample living in neighborhood A, 150, to estimate what proportion of the whole 1 million live in neighborhood A. Mathematics portal would have different probabilities of being chosen if the four sample sizes are not proportional to the population. However, the test is done in the same way. In cryptanalysis, the chi-squared test is used to compare the distribution of plaintext and possibly decrypted ciphertext. The lowest value of the test means that the decryption was successful with high probability. 11-12. This method can be generalized for solving modern cryptographic problems. 13. In bioinformatics, the chi-squared test is used to compare the distribution of certain properties of genes, e.g., genomic content, mutation rate, interaction network clustering, etc., belonging to different categories, e.g., disease genes, essential genes, genes on a certain chromosome, etc. 4. Analysis of variance. Analysis of variance, ANOVA, is a collection of statistical models and their associated estimation procedures, such as the variation among and between groups used to analyze the differences among means. ANOVA was developed by the statistician Ronald Fisher. ANOVA is based on the law of total variance, where the observed variance in a particular variable is partitioned into components attributable to different sources of variation. In its simplest form, ANOVA provides a statistical test of whether two or more population means are equal, and therefore generalizes the t-test beyond two means. In other words, the ANOVA is used to test the difference between two or more means. History. While the analysis of variance reached fruition in the 20th century, antecedents extend centuries into the past according to Stigler. 1. These include hypothesis testing, the partitioning of sums of squares, experimental techniques and the additive model. Laplace was performing hypothesis testing in the 1770s. 2. Around 1800, Laplace and Gauss developed the least squares method for combining observations, which improved upon methods then used in astronomy and geodesy. It also initiated much study of the contributions to sums of squares. Laplace knew how to estimate a variance from a residual rather than a total sum of squares. 3. By 1827, Laplace was using least squares methods to address ANOVA problems regarding measurements of atmospheric tides. 4. Before 1800, astronomers had isolated observational errors resulting from reaction times, the personal equation, and had developed methods of reducing the errors. 5. The experimental methods used in the study of the personal equation were later accepted by the emerging field of psychology. 6. Which developed strong, full factorial, experimental methods to which randomization and blinding were soon added. 7. An eloquent non-mathematical explanation of the additive effects model was available in 1885. 8. Ronald Fisher introduced the term variance and proposed its formal analysis in a 1918 article on theoretical population genetics, the correlation between relatives on the supposition of Mendelian inheritance. 9. His first application of the analysis of variance to data analysis was published in 1921, Studies in Crop Variation I. 10. This divided the variation of a time series into components representing annual causes and slow deterioration. Fisher's next piece, Studies in Crop Variation II, written with Winifred Mackenzie and published in 1923, studied the variation in yield across plots sown with different varieties and subjected to different fertilizer treatments. 11. Analysis of variance became widely known after being included in Fisher's 1925 book Statistical Methods for Research Workers. Randomization models were developed by several researchers. The first was published in Polish by Jerzy Neyman in 1923. 12. Example. No fit, young versus old, and short-haired versus long-haired. Fair fit, pet versus working breed and less athletic versus more athletic. Very good fit, weight by breed. The analysis of variance can be used to describe otherwise complex relations among variables. A dog show provides an example. A dog show is not a random sampling of the breed, it is typically limited to dogs that are adult, purebred, and exemplary. A histogram of dog weights from a show is likely to be rather complicated, like the yellow-orange distribution shown in the illustrations. Suppose we wanted to predict the weight of a dog based on a certain set of characteristics of each dog. One way to do that is to explain the distribution of weights by dividing the dog population into groups based on those characteristics. A successful grouping will split dogs such that a, each group has a low variance of dog weights, meaning the group is relatively homogeneous, and b, the mean of each group is distinct. If two groups have the same mean, then it isn't reasonable to conclude that the groups are, in fact, separate in any meaningful way. In the illustrations to the right, groups are identified as x1, x2, etc. In the first illustration, the dogs are divided according to the product interaction of two binary groupings, young versus old, and short-haired versus long-haired, e.g., group 1 is young, short-haired dogs, group 2 is young, long-haired dogs, etc. Since the distributions of dog weight within each of the groups, shown in blue, has a relatively large variance, and since the means are very similar across groups, grouping dogs by these characteristics does not produce an effective way to explain the variation in dog weights. Knowing which group a dog is in doesn't allow us to predict its weight much better than simply knowing the dog is in a dog show. Thus, this grouping fails to explain the variation in the overall distribution, yellow-orange. An attempt to explain the weight distribution by grouping dogs as pet versus working breed and less athletic versus more athletic would probably be somewhat more successful. Fair fit. The heaviest show dogs are likely to be big, strong, working breeds, while breeds kept as pets tend to be smaller and thus lighter. As shown by the second illustration, the distributions have variances that are considerably smaller than in the first case, and the means are more distinguishable. However, the significant overlap of distributions, for example, means that we cannot distinguish x1 and x2 reliably. Grouping dogs according to a coin flip might produce distributions that look similar. An attempt to explain weight by breed is likely to produce a very good fit. All Chihuahuas are light and all St. Bernards are heavy. The difference in weights between setters and pointers does not justify separate breeds. The analysis of variance provides the formal tools to justify these intuitive judgments. A common use of the method is the analysis of experimental data or the development of models. The method has some advantages over correlation. Not all of the data must be numeric, and one result of the method is a judgment in the confidence in an explanatory relationship. Classes of models. There are 3 classes of models used in the analysis of variance, and these are outlined here. Fixed effects models. The fixed effects model, class 1, of analysis of variance applies to situations in which the experimenter applies one or more treatments to the subjects of the experiment to see whether the response variable values change. This allows the experimenter to estimate the ranges of response variable values that the treatment would generate in the population as a whole. Fixed effects versus random effects. Random effects models. Random effects model, class 2, is used when the treatments are not fixed. This occurs when the various factor levels are sampled from a larger population. Because the levels themselves are random variables, some assumptions in the method of contrasting the treatments, a multivariable generalization of simple differences, differ from the fixed effects model. 13. Mixed effects models. A mixed effects model, class 3, contains experimental factors of both fixed and random effects types, with appropriately different interpretations and analysis for the 2 types. Example. Teaching experiments could be performed by a college or university department to find a good introductory textbook, with each text considered a treatment. The fixed effects model would compare a list of candidate texts. The random effects model would determine whether important differences exist among a list of randomly selected texts. The mixed effects model would compare the fixed, incumbent texts to randomly selected alternatives. Assumptions. The analysis of variance has been studied from several approaches, the most common of which uses a linear model that relates the response to the treatments in blocks. Note that the model is linear in parameters but may be nonlinear across factor levels. Interpretation is easy when data is balanced across factors, but much deeper understanding is needed for unbalanced data. Textbook analysis using a normal distribution. The analysis of variance can be presented in terms of a linear model, which makes the following assumptions about the probability distribution of the responses: 15, 16, 17, 18. Independence of observations. This is an assumption of the model that simplifies the statistical analysis. Normality. The distributions of the residuals are normal. Equality or homogeneity of variances, called homoscedasticity. The variance of data in groups should be the same. The separate assumptions of the textbook model imply that the errors are independently, identically, and normally distributed for fixed effects models, that is, that the errors are independent and. Randomization-based analysis. In a randomized controlled experiment, the treatments are randomly assigned to experimental units, following the experimental protocol. This randomization is objective and declared before the experiment is carried out. The objective random assignment is used to test the significance of the null hypothesis, following the ideas of C.S. Peirce and Ronald Fisher. This design-based analysis was discussed and developed by Francis J. Anscombe at Rothamsted Experimental Station and by Oscar Kempthorne at Iowa State University. 19. Kempthorne and his students make an assumption of unit treatment additivity, which is discussed in the books of Kempthorne and David R. Cox. 2021. Unit treatment additivity. In its simplest form, the assumption of unit treatment additivity, NB1, states that the observed response from experimental unit when receiving treatment can be written as the sum of the unit's response and the treatment effect, that is 22, 23, 24. The assumption of unit treatment additivity implies that, for every treatment, the TH treatment has exactly the same effect on every experiment unit. The assumption of unit treatment additivity usually cannot be directly falsified, according to Cox and Kempthorne. However, many consequences of treatment unit additivity can be falsified. For a randomized experiment, the assumption of unit treatment additivity implies that the variance is constant for all treatments. Therefore, by contraposition, a necessary condition for unit treatment additivity is that the variance is constant. The use of unit treatment additivity in randomization is similar to the design-based inference that is standard in finite population survey sampling. Derived linear model. Kempthorne uses the randomization distribution and the assumption of unit treatment additivity to produce a derived linear model, very similar to the textbook model discussed previously. Cautions. Balanced experiments, those with an equal sample size for each treatment, are relatively easy to interpret. Unbalanced experiments offer more complexity. For single-factor, one-way, ANOVA, the adjustment for unbalanced data is easy, but the unbalanced analysis lacks both robustness and power. 57. For more complex designs, the lack of balance leads to further complications. The orthogonality property of main effects and interactions present in balanced data does not carry over to the unbalanced case. This means that the usual analysis of variance techniques do not apply. Consequently, the analysis of unbalanced factorials is much more difficult than that for balanced designs. 58. In the general case, the analysis of variance can also be applied to unbalanced data, but then the sums of squares, mean squares, and F-ratios will depend on the order in which the sources of variation are considered. 39. ANOVA is, in part, a test of statistical significance. The American Psychological Association and many other organizations holds the view that simply reporting statistical significance is insufficient and that reporting confidence bounds is preferred. 51. Generalizations. ANOVA is considered to be a special case of linear regression, 59, 60, which in turn is a special case of the general linear model. 61. All consider the observations to be the sum of a model fit and the residual error to be minimized. The Kruskal-Wallis test and the Friedman test are nonparametric tests which do not rely on an assumption of normality. 62, 63. Connection to linear regression. Below we make clear the connection between multi-way ANOVA and linear regression. Linearly reorder the data so that TH observation is associated with a response and factors. Where denotes the different factors and is the total number of factors. In one-way ANOVA and in two-way ANOVA. Furthermore, we assume the TH factor has levels, namely,